Another way of writing complex numbers is what we call mod-arg form. Mod stands for modulus. Modulus is something you already know, maybe you don't realise it. It's essentially absolute value. It's the length of the vector OZ, the vector. Okay, so there's our complex number x plus iy. At the moment it's a single point, but if I was to create the position vector, there it is there. Modulus is basically the length of that vector, or distance from the origin if you like. As I say, that is exactly what absolute value is when you think about it. Absolute value of a number is its distance from the origin. We can work it out with a bit of Pythagoras, and there it is again. This x squared plus y squared, this sum of two squares. There'll be a square root of that, of course, because we're talking about a distance, and it's symbolised with the absolute value signs. So modulus of z is the square root of the sum of the squares. The other piece of information is the argument. Again, we can tie that back with vectors, because the other thing a vector had was direction. So the angle our vector makes with the x-axis, the direction of the vector in other words, that is the argument of a complex number. Now, inverse tan of y over x would calculate that. Now there is a notation. Notice here I've written little a, and here I've written capital A. There is a difference between the two. When you have capital A, that's what we call the principal argument. That's what we use most of the time. And it's when you put the answer for the angle in between pi and minus pi. If it's just little a, then we call it, well, it's arbitrary. Sure, angles, you can keep going round and round and round and keep adding another 360 degrees or 2 pi radians, and it's still the same angle when you sub it into sine and cosine and so on. So we tend to go with the capital A one, even if it doesn't say capital A. However, if they say little a, then it's usually, well, it's okay. If they ask for arg z and it's little a, you don't have to get it back to its principal argument. But if they do put capital A, then they're insisting on it. Let's have a look at this then. So 4 minus 4i, what is its modulus and argument? Modulus, square root, sum of the two squares, and we end up with 4 root 2. The argument. Now I haven't written it, you'll notice, as -1. I've written it as -4 on 4. That's to highlight to me that the imaginary part is negative and the real part is positive. Now I write it as -1. Now, quite possibly that first line is something I'm doing in my head, but it's really important I know which quadrant we're in so I get the right angle, because a calculator, when you're dealing with inverse tan, will only give you positive or negative acute angles. So where are we? We're in the fourth quadrant, so actually we are looking for that negative acute angle. So minus pi and 4. Had it have been in, say, the second quadrant, the calculator would still give me the answer, negative pi and 4. But we're looking for the positive obtuse angle, so we'd have to convert that over. So you've got to be careful with that when we're looking for our arguments. Every complex number can be written in terms of its modulus and argument, and again, it will be unique. So only one complex number can have that particular modulus and argument as a combination. Z equals x plus iy, written in our Cartesian form using x and y coordinates. Now, we can calculate the Cartesian coordinates if we know the modulus and argument, because bit of trig, x would be r cos theta, y would be r sine theta, which I could combine that way because they've got a common factor of r. The mod arg form then is when we write it like that. So r outside of cos theta plus I sine theta, that is mod arg form. It's written in terms of its modulus and its argument. You will see this abbreviation used to save time, cis, because the angle is going to be the same for both of them, rather than having to write it twice. It's very often used. Steer clear of it, unless you really need to. Reason? It's so easy to write cos instead of cis, or cis instead of cos, because you're so used to writing cos. It's very easy to write the wrong one down when you don't mean it. But you will see I will use cis from time to time as well, because sometimes it is quicker. Same as sometimes when I'm solving trig equations or factorising or expanding, I'll write C for cos and S for sine, rather than having to write the whole thing out each time. Remember, r is representing the modulus, theta is representing the argument. Okay, so back to 4 minus 4i. If I was to write that in cis theta form, 4 root 2 cis minus pi on 4. So cos minus pi on 4 plus I sine minus pi on 4. So let's do a different one. Root 3 plus I. You're going to find these numbers come up a lot because they're the exact values. So with tan, you had 1 on root 3 and root 3 and 1 and things like that. Okay, modulus for this one turns out to be 2. The argument, inverse tan of 1 on root 3. Which quadrant am I in? Well, they're both positive. So I'm in the first quadrant. I'm dealing with an acute angle here, and that's pi on 6. Again, tend to go with radians now. Radians is what we tend to deal with. Unless they specify other words, unless maybe it's I don't know, some sort of practical problem. It probably makes more sense to say I'm firing something at 45 degrees rather than saying I'm firing at pi on 4 radians. But other than that, we generally go with radians. Certainly once we get to deal with calculus, we definitely use radians. And so there it is. Root 3 plus I is 2 cis pi on 6. Going back the other way, well then that's when it really is useful to have it in the other form, because it tells me exactly what I've got to do. It's 6 times the cosine of pi on 6 plus I times the sine of pi on 6. Pi on 6 is 30, so we get root 3 on 2 plus a half I, expand it out, 3 root 3 plus 3i. So some relationships which allow us to play with complex numbers when they're in this form. If you're finding the modulus of 2 complex numbers multiplied together, again, the order is up to you. You can multiply them together first, then find the modulus, or you can find the modulus of each individual one and multiply that. It works both ways. However, the argument is not like that. The argument, we actually add the arguments together. And that's all to do with this idea of rotation being multiplication. Remember yesterday I said if we multiply by I, it's like we've rotated the picture 90 degrees. So we're adding an angle on. And that's what we're doing here with the argument. We're actually adding the angles together. It's all to do with index laws actually, because you remember with things like that, when you multiply, you add the powers and things like that. It all comes back to that. Multiplication rotates our vector by the argument. That's what we're essentially saying here. In the visual picture, we'd be rotating it. Going to prove it. So Z1, I'll call that R1 cis theta 1 and Z2 R2 cis theta 2. Going to multiply these two things together. Well, the R1 and R2, that's nice and easy. That's just numbers. And inside, we end up with this expression here. Oh, hang on a sec. Look at this pattern. Just look at the real part. It goes cos, sine, sine. We've seen that before. Look at the imaginary one. Sine, cos, sine. Ah, hang on. Cos, sine, sine. If it's not the sine, it's not the sine. Whereas sine, cos, sine, if it's the sine, it's the sine. Actually, look what we've just shown. The modulus of Z1, Z2 turned out to be R1, R2, which is what we were expecting, because that is modulus of Z1 times modulus of Z2. The argument of Z1, Z2 turned out to be theta 1 plus theta 2. Again, what we were expecting. Argument of Z1 plus the argument of Z2. Now it follows, I just did it with 2 numbers, but obviously if we had many numbers, we could just apply that over and over again. So if I've got, I said n there, but I don't know, you've got 10 complex numbers you're multiplying together. It might be easier just to find the individual one of each one and then just multiply that together. And the argument, we would just add them all together, however many we got, we just add them all together. Division, very similar. You could do the division first, then find the modulus, or find the modulus of each one individually, then divide. But with the arguments, we subtract. Again, just like index laws, we subtract. And then this one would follow too. If you had something like this, Z1, Z2 divided by Z3, Z4, again, you could find the individual ones and just go with that pattern. And with the arguments, well, whichever ones are being multiplied together, or whichever ones are on the top of the fraction, if you like, will be positive, and whichever ones are on the bottom of the fraction, because that's what we're dividing by, they would end up being negative when we put them all together. When we're dealing with powers, if you think about z to the power of n, all you're really saying is z times z times z times z times z times z times z times, and so on. And we've already got a rule to handle that. So we know that that will just be the modulus of z to the power of n. And with the arguments then, I must have ended up with n lots of them because I'm going to add them all together. But if I've got n of them, well, I end up with n arguments of z. Notice it hasn't asked for the actual answer to the question. It's simply asked what's the modulus of an argument. So it's going to be quicker, rather than actually finding the answer, to just deal with each individual bit. Now the modulus, then, we'll just find the modulus of each bit. 5 plus I, square root of 5 squared plus 1 squared. Minus 2 minus I, square root of minus 2 squared plus minus 1 squared. And on the bottom of the fraction, we'll end up with the square root of 3 squared plus 2 squared. Oh, how nice. 13 goes into 26. That was lucky. So we end up with the square root of 10 as that. And that's a heck of a lot quicker than actually working out the answer and then finding the modulus. Now, the argument, I'm going to have to go to degrees with this one because they aren't exact values. I'm not going to get a nice neat pi on something. So I'll go to degrees. But inverse tan of 1/5. Now 1/5, first quadrant, so I know I've got the acute angle, 11 degrees 19. Notice here the inverse tan, I wrote it as -1 on -2 rather than a half, because that's reminding me, hang on, this one is over there in the third quadrant. So I'm looking for a negative obtuse angle. So I've got minus 153 degrees 26, and the last one there, well, they're all positive. So again, we're in the first quadrant, 33 degrees 41. We end up with minus 175 degrees 48. We could now get an approximation for the answer, but it would be an approximation because of this angle by putting it back into the r cos theta plus I sin theta formula now, and bang, we could get the answer to that question. But as I say, it would be an approximation because of the size of the angle we're dealing with there. Shifting the reference point, okay? In our Cartesian plane, the reference point doesn't necessarily have to be the origin. We saw that in vectors. Now, because I'm now thinking about a complex number as possibly a vector, well, then I might want to shift it. See, when we did this sort of question in Cartesian geometry, we said, well, we know we've got a circle, center has been moved from the origin to the point 1, 2. And we can do exactly the same idea. So here's our Argand diagram, there's our point, x plus iy, and we know we've got this position vector, its modulus is z, that's how far it is from the origin, and that's the angle it's going to make, its direction vector. If I was interested in this expression, z minus w, then I can do exactly the same thing. The modulus of z minus w is simply the distance from z to w. It's the length of that vector, head minus tail, z minus w. That will be the distance from z to w. So that's modulus, and the argument will be the direction of that vector. So whatever angle that makes with the horizontal would then tell me the direction of this new vector, z minus w. I don't actually have to anchor it to the origin. I can use, instead of position vectors, I could use displacement vectors. It's fine. That's the beauty of vectors. 1D.